Our goal here is to solve some more trig equations so you can use them as sample problems while you're doing your homework. You can pause the video if you need to review our different techniques that we've talked about. But for each equation, we're going to choose a different algebra method. In our first example, I only see one trig function, and it is to the first power. So I think we can simply isolate it. Let's subtract the square root of 3. Let's divide by 3, and you should recognize this as the rationalized version of this same fraction. And doesn't that look like it comes from a 30, 60, 90 with a short leg? Think of the short leg 1/2 over the long leg, square root of 3 over 2. And the halves would have canceled. So do you recognize this as a triangle where the vertical leg is the short leg and the horizontal leg is the long leg? Notice that we want tangent to be negative, so let's think about what quadrants we must be in. In quadrant 2, if I draw that 30, 60, 90 with short leg of 1/2, long leg square root of 3 over 2, the x-coordinate is negative, but the y is positive, so that would work. And we also have that same 30, 60, 90 in quadrant 4, where the y-coordinate is negative, but the x-coordinate is positive. So we've got these two angles. So the first angle, picture it as an angle of rotation. So x, the first angle that we might have, is 5/6 pi. And the second angle in quadrant 4, so this angle that rotates all the way around, 11/6 pi. And now why wouldn't I put negative 1/6 pi? Well, remember our directions ask for solutions in the interval from 0 to 2 pi. So again, notice that they don't want us to answer with negative 1/6 pi. Indeed, that would be the same location. It's coterminal, but we're asked to give our angles this time with values of 0 to 2 pi. Okay, let's move on. Here we see that we have sine squared. So I'm going to move the constant to the other side, and then I would take the square roots of both sides. But immediately I would see here that this is an imaginary number. You could, in fact, write it as plus or minus 2i. Trigonometry never gives us imaginary numbers, so we know that there are no solutions here. Here's a similar example, though, where we have a trig function squared. But let's move the 12 to the other side first and divide by the 3. And then we can take the square roots of both sides. Don't forget the plus or minus sign. And now let's think how we can solve this equation here. What angles have a secant of plus or minus 2? I find it much easier to use its reciprocal. If the secant is 2 over 1, then the cosine is 1 over 2. And that I recognize from our 30, 60, 90 triangle again. That would be the short leg of a 30, 60, 90. So do you see that this triangle gives us a cosine, an x-coordinate of 1/2? And likewise, this angle gives us a cosine of 1/2. And for the negative 1/2, we could have the matching angles over here. So we're going to get 4 different 30, 60, 90 triangles, and each one of them will give us a cosine of either positive 1/2 or negative 1/2. So let's write our 4 angles. We would have pi over 3. I'll scroll here to get more room. We would have 2/3 pi. We would have 4/3 pi. And last, in quadrant 4, we would have 5/3 pi. Now you could write this as a solution set as well. That would be fine. So either way of writing your answer. But you'll get some good practice reviewing the unit circle as you do these problems. Okay, moving on to example 8. Here I see a sine squared and a sine to the first power, and I have a constant. So something squared, something to the first power, and a constant makes me think of a quadratic form where I might be able to factor. If you couldn't factor this, then you would go to you'd go to quadratic formula. Here I think that we can reverse FOIL. 2 sine x times sine x would give us 2 sine squared. And we want the middle term to be a negative, so I think I want a negative 1 here and a positive 1. Check it out here if you FOIL, do the outside and inside combinations. Work out to give us this quadratic polynomial terms of sine, and that works. So now we've got our zero product property. If these two parentheses have a product of 0, either the first parenthesis is equal to 0 or the second parenthesis is equal to 0. And then we're going to isolate our sine values. So here we're looking for angles that have a sine of negative 1/2. Here we're looking for angles that have a sine of positive 1. So where do we see a sine of negative 1/2? That would be our 30, 60, 90s in quadrant 3 and quadrant 4. So here we could have x is equal to 7/6 pi, or x is equal to 11/6 pi. And where is the sine equal to positive 1? That's our quadrant angle. There's no triangle here. It turns into just this segment. So the only place where the y-coordinate is equal to 1 is at pi over 2. So we have 3 solutions for this equation. And one more example. Here I have cosine squared, and I have a cosine to the first power. I see a typing error as I look at this. This equation should have a 0 on this side. What I wanted to get at here was a different type of factoring. So here we don't have a trinomial. We have just this binomial. But notice that cosine x is a GCF. So if I factor a cosine to the first power out of 2 cosine to the second power, again, notice if I distribute, I'll get back to this term. And from the second term, we factored out the cosine x, so this would just give us a square root of 3. So now we've got our zero product property again. If two globs have a product of 0, then either the first term must be equal to 0 or the second term must be equal to 0. And we know the places where cosine is equal to 0. Cosine is the x-coordinate on the unit circle. So these are the 2 quadrant angles where the cosine is equal to 0. So pi over 2, or 3/2 pi. And here we need to isolate our cosine function before we can solve. And we'll divide by 2. And that looks like the long leg of a 30, 60, 90. And we want it to be the cosine. So can you picture that these are the 2 places on the unit circle where the cosine, the x-coordinate, is the long leg of a 30, 60, 90. So this would be at pi over 6. And in quadrant 4, it would be at 11/6 pi. Again, negative 1/6 pi isn't the wrong place. Remember, though, that our solutions are to be in the first positive revolution. So we were asked to give only solutions in this interval, and that's why I chose 11/6 pi rather than negative 1/6 pi as the name for that angle.